So may I know you are getting my screen?
Yes, you can see your screen now. Thank you.
Okay, thank you
You
so
may
much.
start now.
Thank you so much, Dr. Chan. First, I would like to extend my warm welcome to all of you here on the happy eve of this 6th International RSU Conference 2021. And this is my second time going to be present from this platform. And I'm really happy because the chairperson is basically my senior, or you can say this is my teacher, Dr. Moonjin Shan from my lab. And unfortunately, we have missed him and he has left us and he joined to the Monash University. We are missing to him. My special thanks goes to the organizing committee and the host person of this conference. And we are really happy to join this conference and have a collaboration with the Research University. So today I am here to share some information, some knowledge, or some outcomes of my part of research that are related to the study of heat transfer and friction loss of nanofluid suspension flow in circular pipe heat exchanger. The subject line goes to the study of the heat transfer improvement by using different heat exchangers and the different nanofluids. As the engineering industries, we know that facing a lot of problems regarding cooling and heating. So there is still some kind of conventional nanofluids like water, distilled water, e.g. PG, diathermic oil, palm oil, etc. are being used for the heat transportation. So they have some limitations. To improve them, there is immense need of some alternative heat exchanging liquids. That's why the efforts are needed to do some work in the field of nanofluids. So keeping in view all these things, we would prefer that the nanofluid is an emerging area that could be used in the improvement of heat transfer by using different heat exchanger or different nanofluids. So the today presentation, basically, as usual, the introduction, literature view, problem statement, research objective, methodology, result and discussion, references, acknowledgement, vote of thanks. As I have graduated recently, so still I feel that I am a research student still. So that's why I'm here to share some outcomes of my research. As all of us, we know that nanoparticles, basically, we are talking about the nanofluids. We are using nanofluid. So we are aware that the nanoparticle whose particle size is less than 100 nanometer and also surrounded by an interfacial layer that they can nominate the specific size and shape. So the nanofluids are basically dilute liquid suspension of nanoparticles with at least one of their principal dimensions smaller than 100 nanometer. The fluids prepared by particles having size in nanometer are called nanofluids. Such fluids are colloidal suspension of different nanoscale particles in base type fluids. So from previous investigation, nanofluids have been found to possess enhanced thermophysical properties such as thermal conductivity, thermal diffusivity, viscosity and convective heat transfer coefficient compared to those of conventional base fluids like water, e.g. PG, glycerin, palm oil, and transformer, etc. The nanofluid basically categorized in different categories, but here I'm just showing to few of them: the metal oxide based, the composite fluids, carbon based, ceramic based. There are so many. Another new field has been introduced in the nanofluid area, that is magazine based nanofluids. But still the work is going on in these areas. So the potential applications of nanofluids. As you can see here, the heat transfer applications, automotive applications, electronic applications, biomedical application, other application. So basically we are focusing on heat transfer application. Specifically in my case, I'm going to improve the energy transportation in terms of heat transfer by using different nanofluids. So I'm focusing on heat transfer application. So there is an important question that why we are doing this research, because as I collected some data from Science Direct since 1995, the first conference paper was published in 1995 on the nanofluid. From there, you can see this graph is showing that the linearly every year number of publication in this field is going on. So because until so far, still there is a research gap and potential in this field, and can do a lot of work in this field. So all these things make us confident that the field is still new and emerging field. So why we are using nanofluids, why we want to do the improvement, heat transfer improvement? Basically, what is the problem? The problem basically energy crisis is a burning issue. Scientists and researchers had tried most of their efforts to enhance performance of heat exchangers by varying process parameters. Heat exchanger tube materials and alteration of surface morphology by developing different efficient thermal conductivity and coatings. Efforts are needed to find out new avenues for the efficient recovery of energy. Non-comprehensive study to check the important parameters on nanofluid flow in circular pipe. So optimization of synthesis and preparation protocols for the nanofluid. So you can see here, some kids are trying to solve the problem, and I am one of them and trying to solve this issue. So objective of my research, basically I was focusing on two objectives, that is optimization of the parameters of synthesis technique for nanoparticle preparation and the subsequent synthesis of nanofluids to check the effect of their shape and size on heat transfer. Particularly, I was working on the synthesis of my own nanoparticle, then disperse in the any kind of base fluid like water, ethylene glycol, and mixture of water and ethylene glycol. So the current research work, the current paper, basically I was working on the graphene oxide and distilled water-based nanofluid. Here I would like to mention that the graphene oxide I used to synthesize by using modified Hammer method. So the methodology, because as I was focusing on the synthesis of the nanoparticles, my own nanoparticles, then definitely I would like to share that which techniques I'm going to use for synthesis. As we know that here are few important techniques for the synthesis of particle precipitation, sonochemical, hydrothermal, salt gel, eco-friendly method also. So basically I'm focusing on sonochemical method due to some specific reasons. So here synthesis of graphene oxide nanoparticles. Sorry, just a minute. I'm really sorry. I think some construction work is going on the level and there is some lights. And Dr. Shan, I think, knows.
That's fine. Yeah, please just continue. No worry.
Okay. So the synthesis of graphene oxide, and we were using a modified Hammer method. This is the line flow of the synthesis. Basically, we have the raw material like graphite flakes, and then we have the strong acid, sulfuric acid, then we have the potassium permanganate, and according to the required percentage, we edit it, we sonicated, mix it, stir it, and after passing all these three steps, we come up to final this product in form of the graphene oxide nanofluid. So here you can see the schematic diagram of the synthesis of the graphene oxide. So we have the graphite flakes, then we use sulfuric acid, and we put it in the ice bath, and we put the potassium permanganate to control the reaction. And finally, addition of the water, then finally the hydrogen peroxide, we used it here. And finally, we got it in such a way. And it's a really difficult to wash the graphene. So basically the most important step is the washing of the graphene. After washing, we got in the powder form. Then finally refined powder, from that powder we can disperse in the water and we can make it the nanofluid according to our required weight percent concentrations. So after synthesizing the graphene oxide, definitely because we synthesize it, then there is a need to be characterized for different characterizations like FECM analysis, XRD analysis, UV-Vis analysis, and FTIR analysis. And all these facilities we have in University of Malaya, and we can have it here. So in shortly, these all characterization confirms that the synthesis was okay. So we got our graphene oxide product. Once we got the graphene oxide product, then definitely now we are going to our experimental side. We want to prepare our nanofluid. So for the preparation of nanofluid, there are some important techniques that could be used. One-step method, two-step method. And nowadays, our lab is also working on the eco-friendly functionalization method, surface functionalization. So in my case, I'm using the two-step method due to some reasons. So my preferred weight percent concentrations are for 0.025%, 0.05%, 0.075%, 0.1%. So according to the percentage and the base fluid, we have the distilled water. That one is the minimum is the 7 liter. That is the requirement of our experimental setup. So here we have the graphene oxide nanoparticle, base fluid water, then direct mixing by using ultrasonication, by setting different parameters like pulse time, like the probe temperature, like the amplitude, and on-off time. There are a lot of parameters that have to be adjusted here. Finally, we got the 4 different weight concentration of GO and distilled water-based nanofluids. After preparing my nanofluid, then I will come to the experimental setup, and you can see here the schematic view, tutorial view of my this experimental setup, and we set it in heat transfer testing with different heat exchanger like circular, sphere one, and angular test section. In my case, I had to work on circular and sphere one and their comparison by using different nanofluids, single fluid, binary, and composite nanofluids. And here you can see the schematic diagram of the complete this setup. And basically, this is, you can see our heat exchanger wrapped by the external heater and having some thermocouples, K-type thermocouples. And list of the all other important connections and important parts of this experimental setup. So shortly, because here I'm going to present about I'm using scale heat exchanger. So based on a scale heat exchanger, after running the experiment according to the specific flow rates, and in my case, I prefer to do the work in laminar flow, and I choose the 8 different flow rate. And according to that, I calculated the different velocities. And my target was that I want to see the heat transfer improvement. So in that case, here you can see the graph showing that we have the 4 concentration and the base fluid as well in their comparison. So the graph is showing that the 0.1 weight percent concentration means the highest weight concentration is giving more heat transfer with increase in Reynolds numbers. Reynolds numbers mean with increase in flow rate. So definitely all the weight percent concentration is giving improvement as compared to the base fluid mean water. But the higher weight concentration is giving more because the maximum presence of solid nanoparticles basically offering the maximum heat transfer improvement. But there is an important question that either how long we can increase the weight percent concentration. It depends upon, as earlier Dr. Shan talked about in his keynote speech, that the weight percent concentration basically also relevant to the pressure drop and increasing or decreasing viscosity of nanofluid. That's why I prefer that the 0.1 weight percent is the optimized one in my case. So maybe if we go for the 1 or 2%, that could be the cause of clogging of the heat exchanger or need a maximum power pump the nanofluid. That would be dropped down the efficiency of heat exchanger. So based on average heat transfer, similarly, we calculated the average Nusselt numbers here, which is showing that in case of the 0.1 weight percent concentration, see the linear trend is going on here, and the maximum Nusselt numbers are increasing here. So after doing this one, we will compare our experimental data with some correlations data like ministry and so it will make us confident that
excuse me, Mr. Dr. Waqar Ahmed. Excuse me that I am interrupt. Dr. Sathapon, Dr. Sathapon, could you turn off your microphone, please? Could you turn off your microphone? Thank you. Thank you. Okay, you can continue. Sorry about that.
Okay, thank you so much. Thank you. So after doing the experimental setup, experimental result, we compare it with some important correlations like Minsky, Desiku, and Bolter, and we are confident that our data is almost similar to those data that. So in case of 0.1 weight percent maximum, we got the 57% of the base fluid of the improvement of heat transfer. So here is the important question. Sometimes the people confuse that the 57% mean more than water. No, 57% mean including water, because we are dispersing nanoparticle in water. So it's the 57% of the base. The important thing is that that was an average heat transfer. In my case, I prefer to calculate the heat transfer on different point of heat exchanger with respect to their distance, because in my test section, I have the 1.2 meter total length of the test section, and we are divided by the each thermocouple is divided by 0.2 meter of the length, and I try to calculate the heat transfer on each point, which is really important to understand this one. So here you can see H1, H2, H3, H4, H5 mean the different point of the heat exchanger. So as the distance is increasing, as the Reynolds numbers are increasing, as the weight percent increasing, the heat transfer is increasing. So that is important. So for different weight concentration, 0.025, 0.05, 0.075, and 0.1 weight percent concentration. And the 0.1 weight percent concentration goes up to the 2800 watt per meter Kelvin, the maximum, the highest one, and the maximum flow rate. So the second part of this work is basically the friction loss and the pressure drop as well, because we are using different weight percent concentration, then definitely we have to be considered the pressure drop as well. That's why we are working on the low weight percent concentration. The maximum is 0.1 weight percent concentration. And here you can see as the weight percent concentration is increasing, the pressure drop is increasing across the heat exchanger, across the test section. Why? When we add the nanoparticle in distilled water, it raises the viscosity of the distilled water. So as we are adding the nanoparticles, it increasing the viscosity. And also with the increase in flow rate, the pressure drop is increasing. On the other end, the friction loss is vice versa. The friction loss for all the weight concentration and the distilled water showing that as the flow rate is increasing, the friction loss inside the heat exchanger is going to be dropped down. So it's showing that the highest friction is 0.01145 at the lowest flow rate, while at the highest flow rate, it's going to be dropped down. Similarly, here you can see I have another sample that is not a part of this this paper, but I just want to share it here. I was using some binary composite here, and here you can see the results of where I try to show that three things. That the one thing is the velocity, distance of the heat exchanger from start point to end point, then the average Nusselt number, and then Reynolds number. So in the case of Reynolds number, the average Nusselt numbers are increasing, and with the axial distance, as the distance increasing, the average numbers are going to be dropped down. So the finally we found that the pressure drop was maximum at 0.1 weight percent concentration, and the friction loss was the less for the 0.025 weight percent concentration, and it's a common phenomenon. So based on these all experimental results, I come up with some conclusions, and the conclusions that the 0.1 weight percent is giving the more heat transfer improvement. That one is the 57% of the base fluid. All the weight percent concentration of the graphene oxide distilled gives improved heat transfer properties in comparison to the base fluid. Based on average and local heat transfer improvement, all the weight percent concentration offers improved Nusselt numbers with an increase in Reynolds. Similarly, most importantly, there is a slight increase in the corresponding friction loss at the lowest value of the Reynolds number, which is about 2.46% at 0.8% concentration. The maximum pressure drop across the circular pipe heat exchanger was been recorded at 0.1 weight percent concentration. So finally, in summary, from this study, we conclude that graphene oxide distilled water-based nanofluid has a high potential to use an alternative heat transfer fluid in the various heat transfer systems. So here are some references, and on the basis of my experimental these results, I'm confident that recently I published an article in Renewable and Sustainable Energy Reviews whose impact factor is 12.10, and I'm really happy that my research basically acknowledging around the world. So my special thanks goes to the University Malaya and their UMRG grant RP045C, and Research Grant GPF 0508, and Institute for Advanced Studies who helped me, who support me to do this all research. And finally, I'm really thankful to the Oxide University and RSU conference to giving us this opportunity to share this knowledge here. Thank you so very much.
All right, thank you very much. So now I will open the floor for questions. Any question from the floor?
Yes, I am. May I ask you one question? I just like to know that had there any problem for the precipitation of graphene oxide in your circulating tube? Have there any problem for accumulation or precipitation of that graphene oxide?
Yes, ma'am. And that's a really important question. Basically, the graphene oxide, because as you know, the graphene oxide like sheets. So my research was that I uses the exfoliated graphene because I sonicated on the high sonication time that I can break it into small pieces. If you use a normal graphene oxide inside that tube, then it definitely will try to be the clog to the drain. So we really need to be broken in the small pieces.
I'm not sure that I understand you well.
Can you repeat your question, please, again?
Yeah, because you could use 0.1% of graphene oxide in water, right?
Yes.
Yes, and because you circulate in the tube pipe, in the pipe, yes. in the circular pipe, I just like to know, have you any question have there any phenomena of precipitation of that graphene oxide accumulated and then precipitate in that tube?
No, so far we are just dispersing in the water or some kind of base fluid and within the specific limit of viscosity. Because that, we have the specific diameter of the tube. Keeping in view that diameter, we cannot go for the maximum flow rate. There is a limitation of the maximum flow rate.
Dr. Waqar, I think Professor Kanda want to ask if the GO, graphene oxide, will deposit on the surface of the pipe or not. I think that's the question. Right.
Oh, yeah. Okay, I understand the question. Cannot be deposited on the surface because it's highly diluted in the water, and I don't think so. There is another phenomena can be used that if the surface is coated internally, then definitely cannot be the stick on the surface also. And as we are using the high pump, for the pumping to the nanofluid, I don't think so. It could be stick on the surface of the heat exchanger.
Thank you so much.
Okay, yeah, thank you. Any other question?
I have one question.
Okay.
Do you think that in long term, because you use graphene nanoparticles, right?
Yes.
Do you think in long term, if you have heat exchanges like this with the graphene nanoparticles, if it circulates in the system many times, do you think is that possible if you damage the pipe?
Yeah, you are asking about the reproducibility or lifetime of this graphene-based nanofluid.
Yeah, that's right.
It's basically depends upon the dispersion and suspension of the graphene oxide nanoparticles in the water. So far now, without using any kind of surfactant or stabilizing agent, at more than 60-70 days, these graphene oxide nanoparticle could be suspended in the water. As long as it's suspended in the water, then there is no worries to be stick inside the heat exchanger. It cannot block the way.
Okay.
And I will be talking about compatibility device. Compatibility devices are
I think someone is asking you.
Yeah, hello. I think it's hello, can you identify yourself first? Hello.
I think someone tried to ask him.
Yeah.
Oh, okay. Ajahn Thamasak, or Dr. Thamasak. Okay.
Okay.
We can't hear you clearly.
Yes.
usually has
Me. Can you come close to the microphone, please?
therefore, the material
Yes. Or you can type in your question, maybe. I'm not sure if you can do that.
The chat is blocked, disabled. If you enable, then right.
only three something is and also choice. This properties that can be
So I'm not really sure anyone would like to ask the questions.
Yeah, sorry, we couldn't get the question from the professor just now, so I'm sorry for that. Probably if no more questions, I have questions actually. Okay. Is it Dr. Waqar, are you ready? Yeah. Is it
Yes, Dr. Chan.
economical to use graphene oxide nanoparticles as working fluids?
Sorry, can you repeat?
Is it economical to use graphene oxide?
Yeah, this is Dr. Shan, important question. At the lab scale, on the lab scale, we can say on the lab scale it could be the economical. As long as still the nanofluids could be commercialized in the market, then we cannot say it's commercial economical in the market. But on the lab scale, it's quite economical. And the way I use to synthesize the graphene oxide, that is definitely economical. Modified method is very common method, and just we need two acids and calcium permanganate and graphite flakes, and we can get the maximum yield by using this method.
Yeah, I think probably you synthesize in the lab is cheaper, but I think if you buy outside, it's not cheaper. Graphene oxide.
Yes, that's
Anyway, okay. I think that's it for your presentation. And let's give a big round of applause to Dr. Waqar for his presentation. Thank you very much.
Thank you so much, all the organizing team and chairperson. Thank you.
Thank you.